Swayam Prabha. Digital India. Educated India.
We will see the next example. It reads that a single stage inner stage of an impulse turbine provided with a single row wheel. The mean diameter of the blade is 800 mm and the speed of rotation is 3000 rpm. The steam issues from the nozzle with a velocity of 300 meter per second and the nozzle angle is 20 degree. The rotor rotates. The rotor blades are equiangular and the blade friction factor is 0.86. What is the power developed in the blading when the axial thrust on the blade is 140 Newton? So in this example, we know we are given with the RPM, so we can find out VB, which is pi d n by 60. This is mean diameter and this is given. So mean diameter is given to us, so for that we can write down 3.14 into mean diameter is 0.8 into RPM is 3000 divided by 60. So this gives VB as 125.6 meter per second. In the example, this is told to us that velocity is 300 meter per second and nozzle angle is alpha is 20 degree. So we can find out using our formula for beta in terms of V and alpha. So V1 sin alpha divided by V1 cos alpha minus VB. So V1 is 300 into sine of 20 divided by 300 into cos of 20 minus 125.6 and then that is 0.656 and this gives us beta is tan inverse of 0.656 and we get beta is 33.3 degree. Now we can make use of this beta to find out VR, since we know V1 sin alpha is equal to VR1 sin beta 1. So this gives us VR1 is equal to V1 sin alpha divided by sin beta 1 and then this gives us VR as 187 meter per second. It is told to us that friction factor is 0.86. So VR2 divided by VR1 is 0.86. So VR2 is equal to 0.86 into VR1 and so we have VR2 is equal to 161 meters per second. Now we know that power developed is, we are given with axial thrust T A and this axial thrust for us is m dot into delta VA. So for delta VA we know we have to make VR1 sin beta 1 minus VR2 sin beta 2, but blades are equiangular. So beta 1 is equal to beta 2. Beta 1 is equal to beta 2. So what we can write? TA is equal to m dot into VR1 into sin beta 1 minus VR1 into KB into sin beta 2 is equal to beta 1. So we have m dot into VR1 sin beta 1 into 1 minus kb. So that we can make use of it, but here left hand side is known to us and this is given as 140 Newton. So 140 is equal to m dot into VR1, which is 187, into sine of beta 1, which is 33.3 degree, into 1 minus 0.86, and this gives us m dot, which is 9.74 kg per second. Now we can make use of it, since our objective is to find out power developed and we need for power developed m dot, and which we have found out. So power developed is m dot into delta VW into VB. So we can make use of it. So this is m dot is m dot into delta VW VR1 cos beta 1 plus VR2 cos beta 2 into VB. So we know, again we can make in terms of kb. So VR1 cos beta 1 plus kb into VR1 into again cos beta 1 into VB. So it is m dot VR1 cos beta 1 into 1 plus kb into VB. So power developed is equal to m dot, which is 9.74 into VR1, which is 187 into cos of 33.3 into 1 plus 0.86 into 125.6, and this gives us answer as 355.84 into 10 to the power 3 watt, and this is equal to 355.84 kilowatt. So this is how we would have solved this example, where we were given with the axial thrust and then we were making use of it to find out the mass flow rate. We will move ahead to the next example, which states that the angles at inlet and discharge of the blading of a 50% reaction turbine are beta are 35 degree and 20 degree respectively. The speed of rotation is 1500 rpm and at a particular stage mean ring diameter is given as 0.67 meter. The steam condition is at 1.5 bar 0.96 dry. Estimate required height of the blading to pass 3.6 kg per second of steam and power developed by the ring. Here very first thing which is given to us is degree of reaction, which is lambda is equal to 0.5, and we know beta 2 is equal to alpha and beta 1 is equal to delta, or what we say, if we name alpha 1 and alpha 2, then beta 2 is equal to alpha 1 and beta 2 is equal to beta 2 is equal to alpha 1 and beta 1 is equal to alpha 2, and this is given to us. So we are told that beta 1 is equal to 35 degree since it is at the inlet, and so this is equal to delta, and beta 2 is equal to 20, so this is equal to alpha. Having said this, we should proceed. We are told that the mean diameter at the height is 0.6 meter and speed is 1500, so VB is equal to pi d n divided by 60, 3.14, d is 0.67 into 1500 divided by 60. So VB for us is 52.62 meters per second. Now for this example to solve, we can make use of the triangle law or sine law for the triangle, where we are having this as V1, this is VR1, and this is alpha, and then this is beta 1. This is beta 1, so this will be 90 minus 180 minus beta 1, and for us beta 1 is 35. So 35, so 180 minus 35 is this 180 minus 35, and then this alpha is given to us as 20 degree. So using this we can find out rest of the things. So we have this angle as 145. So this angle is 145, this is 20. So it tells us that this angle is 180 minus 145 plus 20, and this angle, that's why it becomes 15 degree. So this is 15 degree angle, this is V1 and this is VB. So what we have is alpha is the angle across which we are having side VR1, beta 15 degree angle is this, and for which across which side is VB, and this angle is 145 degree and for which side is V1. So we can write down this, we can make use of this and write down V1 upon sine of 145 is equal to VB upon sine of 15 is equal to VR1 upon sine of alpha, which is 20. So having said this, we can make use of this first and find out V1. So V1 is equal to VB into sine of 145 divided by sine of 15. So we can get V1 from here as 116.6 meters per second, but it is lambda of 50%, so this is equal to VR2. Since we know V1 is equal to VR2, and then we can find out VR1 from here as VB into sine of 20 divided by sine of 15, and this gives us VR1 as 69.54 meter per second, but this is equal to V2, since for 50% reaction VR1 is equal to V2. Knowing this, we can find out delta VW, and delta VW is VR1 cos beta 1 plus VR2 cos beta 2. So VR1 we are knowing now, which is VR1 into cos of beta 1 plus VR2 is basically V2 and cos of alpha is equal to, VR2 is equal to V1 into cos of alpha. So we can either of them we can use, and then we can find out delta VW, and delta VW for us becomes 166.56 meters per second. Now we know that we are supposed to find out the area. For area we can use formula for mass flow rate. Mass flow rate is basically density into area into velocity. So we can make use of this by the fact that it is equal to area into velocity divided by specific volume, where we can write down area as pi d into, which is mean diameter over here, into h of the blade, height of the blade, this is area, into velocity. Velocity is VA, axial velocity, divided by specific volume. So for this formula to use, where we can find out HB, we need VA and specific volume. Specific volume can be found out from the state that it is at 1.5 bar and X is equal to 0.96, and this gives us V1 at that state as 1.114 meter cube per kg from the steam table. So once this is known, we can make use of the fact that VA is equal to V1 sin alpha. So this formula can be rearranged and it can be written as HB is equal to m dot into specific volume divided by pi d into VA, which is m dot. Since m dot is 3.6, so we are knowing that 3.6, specific volume is 1.114, pi is 3.14, d is given to us as 0.67 into V1, and V1 is 116.6 into sine of 20, and this gives us HB, which is basically 0.047 meter, which is 47 meter. So 47 mm. So this is how we can find out first part, which is height of the blade. Now we can find out power developed. Power developed is equal to m dot into delta VW into VB, and delta VW is found out 116.56, so 116.56, and VB is also known 52.62. So we have this answer of power developed will be 31.55 into 10 to the power 3 watt. So power is equal to 31.55 kilowatt. So having said this, we found out both power developed and the height of the blade. In this example, point to be noted that we were not given with any velocity like V1 or VR1, we were given with only one velocity, but we were given with two angles. Then we made use of the sine law of triangle and found out required thing. Then we will go ahead with the next example, which states that speed of rotation of blade group of a 50% reaction turbine is 3000 rpm. Mean blade speed is 100 meter per second. The velocity ratio is 0.56 and the exit angle of the blade is 20 degree. If the mean specific volume of the steam is 0.65 meter cube per kg and the mean height of the blade is 25 mm, calculate mass flow of the steam through the turbine in kg per second. Neglect the effect of blade thickness on the annulus area. If there are 5 pairs of the blades in the group, calculate useful enthalpy drop required and power diagram power. In this example again, what we have is lambda is equal to 50% or 0.5 degree of reaction. So we have beta 2 is equal to alpha and beta 1 is equal to delta or alpha 2 as per the sign convention. And then we are also given with the fact that velocity ratio is 0.56. This is the new thing, which is VB upon V1 is velocity ratio, and that is given as 0.56. Further, for 50% reaction, we have VR1 is equal to V2 and V1 is equal to VR2. So Let us solve this example. We can basically make use of the fact that we are told that mean blade speed is 100 meter per second. So VB upon V1 is equal to 0.56. So we can make use by saying V1 is equal to VB upon 0.56 is equal to 100 divided by 0.56, which is 178.57 meters per second. But as the fact goes, we have V1 is equal to VR2, so VR2 is also equal to 178.57 meters per second. Now we can find out, we are basically needing mass flow rate to be calculated. So for that we will need, as we know, mass flow rate is equal to density into area into velocity. So for this area to calculate, we need diameter, since density can be replaced by 1 upon specific volume, and then area is pi diameter into HB into velocity, which is VA. So here we need diameter, and that diameter we can find out from VB is equal to pi dn by 60, and that VB is 100. So we have D diameter is 2 by pi meter. Since we have pi, 3 pi into D into n is given as 3000 divided by 60 is equal to 100. So we have D is 2 by pi meter. Having said this, we should proceed and then find out m dot is equal to pi into D into HB into VA divided by specific volume, and that specific volume is given as 0.65. So we have pi. D is equal to 2 by pi into HB. HB is given as 25 mm. So 25 into 10 to the power minus 3, and then VA is V1 sin alpha divided by specific volume, which is 0.65. So m dot we can make use, since we can make use of all these things, and we have basically given that blade angle at the exit as 20 degree. So we are given as beta 2 as 20 degree, but that is equal to alpha. So alpha is 20 degree, V1 is calculated, so we can make, so 2 by pi, pi gets cancelled, so we have 2 into 25 into 10 to the power minus 3, V1 is 178.57 into sine of 20 divided by 0.65, and this gives us m dot as 4.69 kg per second. Now we are going to find out other things, enthalpy drop. So for that, first find out beta, since we know tan of beta 1 is equal to V1 sin alpha divided by V1 cos alpha minus VB. So we know V1 178.57 into sine 20 divided by 178.57 into cos 20 minus VB, and VB is equal to 100 meters per second. So this gives us beta is beta 1 is equal to 42 degree. So having this, we can make use to find VR1, and VR1 is equal to V1 sin alpha divided by sin beta. So we have beta 1. So we have VR1 is equal to 91.25 meters per second. Here basically we are using VA1 is equal to V1 sin alpha is equal to VR1 sin beta 1, and then in this process of equation we are getting VR1 is equal to V1 sin alpha divided by sin beta 1. So we can write down delta H moving blade. There is enthalpy drop in the moving blade, and we know in case of reaction turbine there is the enthalpy drop in the moving blade, and in impulse turbine there is no enthalpy drop in the moving blade. Since there is no enthalpy drop in the impulse turbine, and in case of frictionless flow we have VR1 is equal to VR2. Relative velocity does not change, but in case of reaction turbine relative velocity changes. So there is increase in relative kinetic energy, which is basically due to change in enthalpy in the moving blade. So it is half into VR2 square minus VR1 square, which is equal to half VR2 minus VR1 into VR2 plus VR1. So we know VR1 and we know V1, that is equal to VR2 since we have said here. So delta H moving blade is equal to 11.78 kilojoule per kg. So we have delta H complete stage is equal to delta H nozzle or fixed blade plus delta H moving blade, but we are told that it is 50% reaction, so it is 2 into delta H moving blade, so it is 23.56 kilojoule per kg. So there is delta H total, since it is told that there are such 5 rings. So 5 into delta H stage. So we have delta H is 117.80 kilojoule per kg. So we have basically power developed is equal to m dot into delta H total, and we know m dot is 4.69. So 4.69 into 117.8, and this gives us 553.4 kilowatt. So this is how we would have made use of the new things. What we understood over here is this, that velocity ratio is Vb upon V1, and we also should remember that change in relative kinetic energy or increase in relative kinetic energy is enthalpy drop in the moving blade. This also we have made use of. So now we will go ahead with the next example, which states that at a certain point in a 50% reaction turbine, the steam leaving a moving blade row is at 1.5 bar and 0.9 dry. The steam flow rate is 7 kg per second and the turbine speed is 3000 rpm. At entry to the moving blade row, the axial velocity of the flow is 0.7 times at the exit of the row, 0.75 times the mean blade velocity. Okay, the exit angles of both fixed and moving blades are 20 degree measured from the plane of rotation, and height of the moving blade at the exit is 1/10 of the mean diameter. Determine the height of the moving blade at the exit and power developed in the blade row. So in this example we are again told that lambda is equal to 50% is equal to 0.5, so alpha is equal to beta 2 and beta 1 is equal to delta VR1 is equal to V2 and VR2 is equal to V1. Further, we are told that the angles are 20 degree. Exit angles of both fixed and moving blades are 20 degree. That means beta 2 is equal to alpha is equal to 20 degree, and this is what it is given. So we can make use of the known fact of one more thing, that axial velocity of the flow is 0.7 times the mean blade velocity. Axial velocity is VA1 is equal to V1 sin alpha, and that is equal to 0.7 VB, and it is also known that the velocity, axial velocity at the exit of the row is 0.75 the mean blade velocity. So we are knowing VA2 is equal to V2 sin delta is equal to 0.75 VB. Further, it is told that m dot is equal to 7 kg per second. So we know m dot is equal to area into specific volume into velocity. So we have m dot pi d into h b into specific volume into velocity, which is V2 sin delta. Since we are told that properties are at the leaving state, so we are given with V2, and this area is also at the exit. So that is why we are using axial velocity at the exit, and this is axial velocity. So we have m dot is equal to basically 7 is equal to pi into d into hb, but for hb it is told that height of the moving blade at the exit is 1/10 of the mean diameter. So d by 10 into specific volume at exit, we can find out from this state, which is 1.5 bar and 90 dry. From the steam table, if we find out, we will get V is 1.045 into V2 sin delta, and V2 sin delta is also known to us as 0.75 VB. So this is what it is told to us. But further, VB, we know it is equal to pi dn by 60. So this also we can keep here, and then we will have 7 is equal to pi into d by 10 into 1.045 into 0.75 into pi dn, and n is given as 3000 divided by 60. So here we know everything except d, so this becomes an expression of d cube. So we get basically d cube, which is 0.1976. So we get d as 0.528 meter. So we got diameter, or we basically got a mean diameter at the exit. Knowing this mean diameter, we can find out VB, which is pi dn by 60, so which is pi into 582 into 3000 divided by 60, and this is 91.42 meters per second. So we have delta VW is equal to V1 VR1 cos beta 1 plus VR2 cos beta 2. But in general, we can write this expression. However, in case of 50% reaction, the same expression can be written as twice V1 cos alpha minus Vb. So having said this, we know now everything, and we can find out delta Vw from here, and so we have delta Vw is equal to 260.2 meters per second, where we are going to make use of the fact that here we need to know V1, and this is basically found out from this expression, which says that V1 is equal to 0.7 Vb divided by sin alpha. So this we can put over here and then find out delta Vw, and once delta Vw is known, we can find out power, since power is equal to m dot into delta Vw into Vb. So we get power, which is also called as diagram power, as m dot is 7, delta Vw is 260.2 and Vb is 91.42. So we get 166.52 into 10 to the power 3. So it is in watt, which is equal to 166.52 kilowatt. So in this example, we saw that in a 50% reaction turbine, we can convert with the given constraints of the velocities at the exit or at the inlet, and then find out first the expression for diameter, and then make use of that to find out the necessary things. We will move ahead to the next example, which states that a steam turbine is to operate between 150 bar 600 degrees Celsius and 0.1 bar. The bucket velocity is limited to 300 meters per second. Average nozzle efficiency is expected to be 90%, except for impulse stage, for which it will be 95%. Nozzle angles will be assumed as 15 degree for impulse stage and 25 degree for reaction stages. All stages operate close to speed of maximum efficiency. Estimate number of stages required for each case of the following arrangements: all simple, all 50% reaction, a two-stage Curtis followed by a simple impulse stage, a two-stage Curtis followed by 50% reaction. So in this we will go ahead and see. In this example, if we try to plot the TS diagram, then we are told that this state is 150 bar and 600 degree Celsius, and this state is given to us as 0.1 bar. So we can make use of these two states to find out the total enthalpy drop. So for that, let us find out. We will say it as 1 and say it as 2. Okay, but here we should remember that it will have 2 dash and 2, since the efficiencies are different and they are not 100%. So knowing this, first let us find out H1, which is corresponding to 150 bar and 600 degrees Celsius. It turns out to be 3582.3 kilojoule per kg. Similarly, at the same state, we will note down entropy, which is 6.6776 kilojoule per kg Kelvin, and then we can note down H2 dash. Since for H2 dash we are using the fact that S2 dash is equal to S1, and this gives us the X2 dash, which is the dryness fraction at state 2 dash, which is inside the dome, which has equal entropy as 1, and that gives us X2 dash as 0.8 0.04, and this we can make use to find out H2 dash, which is HF plus X2 dash into HFG at 0.1 bar. So we get H2 dash is equal to 2114.9 kilojoule per kg. Knowing this, we can solve first example where all stages are impulse. Now for impulse stages, the nozzle efficiency is given as 0.95, which is 95%. So is 95%. We can find out V1 from here, which is square root of nozzle efficiency into delta H isentropic or delta H dash and into 44.72. Now V1 is equal to 0.95 into H2 dash is 3582.3 minus 2114.9 into 44.72. So for us V1 is equal to 621.2 meters per second. We have to keep this point in mind. We are writing this delta H in kilojoule per kg. That is why we have 44.72 as a number which is outside the square root. So we get velocity in meters per second. But we are told that all the stages work close to optimum. So we have Vb upon V1 in case of impulse turbine as cos alpha by 2. So which is equal to cos of 15, since it is given 15 degree for impulse stages, cos of 15 divided by 2, and then this gives us Vb. We will start the example with first part where all the stages are impulse, and for all the impulse stages we can make use of the fact that we are having Vb upon V1 is equal to cos alpha by 2, since it is told that this close to optimum condition. So we have V1 is equal to Vb into 2 divided by cos alpha. So V1, and we are told that Vb is 300 meters per second. So 300 into 2 divided by cos of 15, angle is given as 15 degree. So we have V1 is equal to 621.2 meters per second. Now we can make use of V1 to find out stage enthalpy drop, since V1 is equal to nozzle efficiency into delta H stage into 44.72. So we can say that V1, which is 621.2, is equal to 0.95 into delta H stage into 44.72, and this gives us delta H stage as 203.1 kilojoule per kg. But we have total delta H is equal to H1 minus H2 dash, and this is equal to H1 is 3582.3 minus we have H2 dash, which is 2114.9. So we have delta H total is equal to 1467.4 kilojoule per kg. So number of stages is equal to delta H total divided by delta H stage. So we have delta H total divided by delta H stage as 7.22. So we have around 8 stages. So we have around 8 stages for impulse turbine. So now we will see for 50% reaction. So for 50% reaction, we know we are having Vb upon V1 is equal to cos alpha. So we have V1 is equal to Vb upon cos alpha, which is equal to 300 divided by cos of 25. So this we would find out Vb V1 from here, and which is 331 meters per second. Again we know V1 is equal to 44.72 into square root of delta H stage divided by 2 into nozzle efficiency. Here we are dividing it by 2 since half of the enthalpy drop of the stage takes place in the nozzle. So that will be giving us V1 velocity, and half will take place in the moving blades. So which was complete delta H in case of impulse, now it becomes delta H by 2 for the 50% reaction, and then this is equal to 331. So we can get delta H stage from the known data for 2 stage is 115.34 kilojoule per kg. So number of stages equal to delta H total divided by delta H stage, and this gives us 1467.4 divided by 115.34, which is equal to around 13 stages. Now we will see a 2-stage Curtis followed by impulse. So but for 2-stage Curtis, in case of optimum, we know Vb upon V1 is equal to cos alpha by 2 into 2. So this is for 2 stage. So this is basically cos alpha by 4. So we have V1 is equal to 4 Vb divided by cos alpha, and then this is equal to 4 into 300 divided by cos 15, since it is 15 degree given in the example. So this is 15. So for that we get V1 as 1242.4 meters per second. So we have V1 is equal to 44.72 into square root of delta H stage into nozzle efficiency, which is Nj, and so we have basically delta H stage. From here we will get delta H stage as 857.58 kilojoule per kg, since we know Nj is 90%, and then we have 44.72 known, V1 is known 1242, and this gives us delta H stage. So we have number of stages is equal to delta H total divided by delta H stage. So it is equal to delta H total, as we know basically delta H total is equal to 1467.4, and then we want one stage of velocity compounded Curtis turbine. So what we will do, we will subtract from here 857, so we will have delta H only impulse simple impulse is equal to 1467.4 minus 857.58. So we have 609.8. So this is the enthalpy drop if we use all the stages after the two stage Curtis as impulse. So we have to find out number of impulse stages. So number of impulse stages is equal to delta H total for impulse divided by delta H stage for impulse. So we have 609.8 and we have found out delta H stage for impulse is equal to 203.1. So this is 203.1. So we have around 3 stages. So one stage Curtis, or rather two stage Curtis, will be followed by 3 stages of simple impulse turbine, where we would be needing 8 stages of simple impulse. Now last we will solve for a row of 2 stage Curtis, and 2 stage Curtis we know, one row of 2 stage Curtis. So we have to find out delta H reaction is equal to this 1467.4 minus 857.58, and this gives us again 609.8, and we know one stage of reaction has 115.4. so number of stages of reaction is equal to delta H reaction total, which is this, divided by delta H stage, reaction stage, and this is equal to 609.8 divided by 115.34. So we have 5.28, which is around 6 stages we need as 50% reaction turbine. So this is how we have seen that if we are having fixed boiler condition and fixed condenser condition, so for that how we would have different number of stage requirement for the different kind of turbines.